In the last example, we considered maximizing the volume of an open box by determining its dimensions, and maximizing volume or minimizing the surface area for fixed volume is a very common application of calculus in industry, where in manufacturing we want to make containers that will hold the most amount given the smallest amount of material required to make them. This keeps operating and manufacturing costs at a minimum, while at the same time providing the most utility for the consumer. Let's take a look at another application of this. In this case, we have an aluminum can. So what are the dimensions of an aluminum can that can hold 40 cubic inches of soda and that uses the smallest amount of aluminum? So we're going to minimize our surface area for a fixed volume. Assume the can is cylindrical and capped on both ends. So here's what we're talking about. So we have a cylinder and we have two circular areas, each of which is pi r squared because the radius is going to be the same anywhere in the cylinder. And then we have the rectangular piece of aluminum which is rolled around the circles, and that has an area of 2 pi r, the circumference of the circle, times the height. And this actually allows us to derive a formula for the surface area of a cylinder. It's 2 pi r squared plus 2 pi rh, adding all of these areas together. But let's start with that surface area formula. So let's make a quick note to ourselves that we are minimizing the surface area, and surface area is going to be equal to 2 pi r squared plus 2 pi r h. Now, you'll notice that surface area has two variables in it. It has an r, the radius, and it has an h, the height. And so another formula that we probably want to think about is volume, since that's what we're talking about. Volume is fixed, and so that will allow us to use the volume formula to find a relationship between r and h, because these two variables are related in that formula as well. So volume is going to be the base pi r squared, which is a circle, times the height. And so now, letting v be equal to 40, why don't we solve for h, and then we can have surface area as a function of r. So this gives us pi r squared h, and h equals 40 divided by pi r squared. And so now let's do surface area as a function of radius, and that's going to be equal to 2 pi r squared plus 2 pi r times h, and in place of h we'll put 40 over pi r squared. Now the pi's cancel, the r cancels, 2 times 40 is 80, and so we can rewrite this now. Surface area as a function of r is equal to 2 pi r squared plus 2 times 40 is 80 over r. Now remember, we want to minimize the surface area, so let's take the derivative. SA prime of r is equal to 2 times 2 is 4 pi r plus, and this is 80 times r to the negative 1, so when I take the derivative we end up with a minus 80 over r squared, and we'll set that equal to 0. So this gives us 4 pi r equals 80 over r squared, and since r not equal to 0, it's legal for me to multiply through the equation by r squared, and that's going to give us 4 pi r cubed equals 80. And then solving for r, we get the cube root of 80 divided by 4 pi, and that is 20 over pi. Now that is approximately 1.853 inches. So that is what the radius is going to be. Now what is the height? Well, we'll go back to our h formula. So h equals 40 over, and you know what, since I've got a pi in here, let me just substitute the exact value. So this would be 20 over pi to the 2/3. It's the cube root squared. Plug that into your calculator. We get 3.707 inches. And so we have our radius, approximately 1.853 inches, and our height, approximately 3.707 inches. And this will give us the desired volume of 40 cubic inches with the least amount of aluminum possible.